Okay, so hello everyone and welcome back to the AI class. What we were saying or discussing before recording, I'm going to say it quickly, is that everyone is encouraged for the rest of the semester to join one of the groups by the end of this week. And for the rest of the semester, there won't be any homeworks. Expect working on one of the projects, which is whether the subset of AI, which is machine learning, or the subset of deep learning. Okay, so you need to finalize your choice about the AI project and join your group, start communicating. The second thing is that what we did last time or before even, we started with the learning phase within AI. So we went from like rules to learning, which is a different process. When we talk about learning, there are different types of learning, from like supervised learning, unsupervised learning, semi-supervised learning, reinforcement learning. So next we say that there are, if we are going to categorize the learning methods, there is three. We started with the first one, which is generative methods, and seen as a first algorithm, the k-means algorithm. And next, we are today going through the Gaussian mixture model. So when it comes to Gaussian mixture models, you are going to frequently see GMM, and here we are going to target or have some learning outcomes, but mainly our motivation is that we are working in the context of clustering. Last time when it was k-means clustering algorithm, we were discussing it's a particular case of hard clustering. And when we say hard clustering, if I have like groups or clusters and I have some point, for example, or data sample, it whether belongs or not to some cluster, which means for hard clustering, each point is associated to one and only one cluster. We cannot discuss that one is belonging to both at the same time, for example. However, there is another way, which is soft clustering. Soft clustering is when we say that every point belongs to multiple clusters with certain degrees. And when we start talking about degrees, this makes us remember the presentations that Zoya did, which was about fuzzy logics. So when we talk about fuzzy logics, if you remember the example that I was showing you first time, if I have like two clusters, whether it belongs or not, this is a hard clustering. But if I'm going to take an example of an element and I am going to check, so this element belongs to this class, let's say 60%. However, it could also belong to the other class with the remaining percentage, like 40%, okay? So this is coming to cover the limitation of hard clustering, which is that there is no probability which can tell us in this case how much a data point is associated with a specific cluster, okay? So this is the example of k-means, which is a hard clustering example. So if we have a sample coming, and last time we said, we are going to say, for example, there are men and women. Someone is entering, given some criteria, given some similarity matrix, distance, or whatever. The k-means algorithm is going whether to put it here or there. However, it's not the case, okay? So this is what we will see today. And before moving, I found this post 2 hours ago. So this is a Facebook page, the Frustrated Researchers. So most of you, if you are going to start loving AI, maybe your LinkedIn or your social media following things are going to take a different direction. Okay, so this is one of the pages that shares really funny content, especially now it's Halloween. So what we see here, it's bow, okay? So this is a ghost. If we take this example, I was just going through this web page. Let me just open it and we'll see together. So what we see here, it's a plot of something which is extremely interesting, which is, oh, it cannot zoom more. Okay, no worries. The ghost function. Hello. So what you see here, is this ghost. So this ghost is, let me say, there is a function that is imitating its representation. This function, as you can see here, it's h of x, which is ghost of x. It's just a function. And if you are going to see this function, it's coming. Here you can see what? It is the normal distribution or the Gaussian distribution, okay? This is on the top of the function. And down, this is the famous sinusoidal-like distribution, okay? So both together are forming this like amazing function. And this is the way I wanted to motivate starting today's class. So what you can see here is that from Gaussian function, you can do many things. From normal distributions, you can think of many things. And when it comes to the Gaussian distribution last time, we were going through this, but we didn't detail this. Okay, so when we seen last time the Gaussian distribution, we seen in the context of AI, when we were discussing probabilities, we also seen when within the fuzzy logic presentation, one way to present the mu function, and now it has multiple use cases. So what we will see now is we are going to revise this, and I believe that everyone is familiar now with the mathematical definition of the Gaussian distribution, where y here presents the probability density function. So it is 1 divided by sigma square 2p. We have exponential function here, minus x minus mu square, and 2 sigma square. So this function must be now, everyone must be familiar with, because last time we seen, even if I am evaluating or taking any random distribution, random variable, sorry, a set of random variables, I have a huge probability that this random variable is going to follow some like normal or Gaussian function distribution. Like, for example, if I'm going to check the results in the exam after grading, mainly there would be like a given number of students, which is the majority here, getting good grades. However, this cannot deny that there would be maybe some students that are not getting good grade, okay? At the end, the sum, or given this distribution, if we want to illustrate with a percentage, we can see that, first of all, this function, it is symmetric, which means if it's going up at some point, it is going down after that with the same way, okay? So, which makes it almost having here similar percentages, and here similar percentages, and here 2.1, 2.1 similar percentages, like 0.1, 0.1 also similar percentages. What you can see here is between, which is important values, like between 2 sigma and minus and plus 2 sigma, we have the majority of the data, which is the sum of all these percentages, mainly 91.4% of the data is like in this interval. Is that clear? So this is now clear for everyone. However, when it comes to Gaussian distribution, we have different parameters, okay? I'm going to say the most important, mainly they are. So we talk about mu, which is the mean, okay? And when we say the mean, it means the mean of all values, which is in the middle, okay, in this case. So here, your mu function is equal to 0, which means these blue, red, and yellow curves or distributions are centered to 0, okay? They have the mu value, which is equal to 0 here. Now, the sigma squared, which is variance. So sigma is standard deviation, okay? And sigma square is, power 2 means is variance, which represents what? Which represents, let's say, the width of this. So if we see here, the one having like maximum value of this like standard deviation. They are related because if the standard deviation is high and if you are going to multiply by itself, it's going to give a high value, okay? So if it's high like this, you can see the plot is having, let's say, huge width here. If, for example, it's not high, like this case or this case, then it's not that huge, okay? So this represents the width of this distribution, and this represents the mu where this distribution is centered. Like, for example, if you take the green plot, it's centered in -2. So the mu value is -2, okay? Is this clear for everyone online?
Yeah, that makes sense.
Because these are the basics. Okay. Now, we said that the function that we've seen so far is given the 1D. However, we can expand this function, and we said this last time, to multiple dimensions. Because, for example, if we take the example of D dimensions, what will happen here is that you are going to have this D, which is going to represent your dimension, okay? So if you are, for example, in the case of 2D, this D is going to be equal to 2. If you are going to divide 2 by 2, so it's going to give you 1, so which is 2p times the rest of the equation, okay? So mu here is the mean and sigma is the covariance matrix that you can see here, and we are going to detail this. So this is an example of representation. It's like a bell, okay? Like I was saying last time, it's the Mexican like hat or that you can wear, okay? So it's this shape where, for example, it's in this case, so the center, it's 0, 0, because you have it like the coordinates you can see here in 0 in this axis, 0 in this axis, okay? And the covariance matrix here is taking these values in this case, okay? So still, we are going to go through examples. For example, now, what we will see. Moving now from that, just understanding the Gaussian distribution, which could be represented whatever the space you have from 1D to multiple dimensions, okay? And now let's consider the 1D case, okay? This 1D case, what we have 3 like Gaussian functions. And what are we doing now? We are performing clustering. So if I'm going to perform clustering and I have for example, some population, I am like plotting the Gaussian functions and I'm getting 3 different Gaussian functions. If I am going to check the points within my x-axis, because I am in the case of monodimensional, okay? So what will happen here? I can understand that these like red plots, red points, they belong to the red cluster represented by this Gaussian function, okay? This like green cluster, it's where these points belong. So what you can see is that within the middle of the distribution, when we are almost projecting points that are having the highest value here, we are sure that these are red. We are sure that these are green. We are sure that these are blue. Why? Because here the probability of belonging is very high. However, here in the side, still we don't know. Sometimes we can consider it belonging to the red and it's belonging to the green. Did you got the idea? So this is our problem now. Now we are performing clustering. We are taking into consideration the knowledge given the Gaussian distribution. And this is called the Gaussian mixture model. It's like you are saying, I'm applying the K-means algorithm. You are going to say, I'm going to apply the Gaussian mixture model, okay? And this is going, given a set of points, to tell you which belongs to which cluster, okay? So we will see an example about this, but just to introduce the concept, the Gaussian mixture model is just a type of machine learning algorithm, like same like K-means or in the context of clustering, okay? So we are going to see this, and next we are going to compare it with the K-means itself. So whenever we are seeing things, keep in mind What can this make me remember, for example, in the case of k-means? So this type of algorithm is used to classify data into different categories based on probability distribution, because the key of this one is probability distribution. For the case of k-means, what was the key?
Distance.
Distance, which is the similarity measure, which is the distance, right? So here what we have, the Gaussian mixture models can be used in many different areas like finance, because in finance, for example, how you can see this like clusters example could be the market value of anything, for example, or okay. Marketing, computer vision, we will see an example of computer vision. In marketing is the value of something. In finance, for example, if you have in banks, you have groups of what we say clients, for example. Those, for example, you want to study the history of their loans. So you can understand that distinguish three different distributions. This is just an example, okay? So what we will see now, it's that first thing is that when it comes to Gaussian mixtures, there is the mathematical background. So now today, mainly there will be a lot of equations. So don't be afraid, it will be simple. So a Gaussian mixture is a function. So we are going now to introduce the function, which is the mathematical keyword. And this one is comprised of several Gaussians, okay? Each one is identified by k from 1 to k, where k is the number of clusters. So you are now familiar with the k-means, and you know your k is the number of clusters. It's the same thing here. And the k here is a very important parameter for the function representing the Gaussian mixture. And each Gaussian, now k in the mixture, is comprised into the following parameters. So for each one, we have mainly three, okay? The first one, we are going to go through these parameters in details. Mu, to define the center. There is the covariance matrix, which is sigma. And there is a mixing probability that defines how big or small is the function going to be, okay? So to see this in details, we mathematically note this with this omega, which is a set of three parameters that are mu, sigma, and theta, right? Yeah, and this is omega, because I'm switching my eye to the last one. So the set is having mu, sigma, and omega. Yeah, right. So which could be you confuse me. So where we can see that the mean is the first one, which is mu. And we know the mean is if you have a set of elements, you have multiple elements like these points. I want to see the mean or the mu function of the red points. How can I get that? I sum them and divide them by the number, okay? So it's very simple. Next, we have the covariance matrix. So for each component here, it represents the shape and orientation of the Gaussian component, okay? So given the data space for sure, and for d-dimensional data sets, this covariance matrix is given by times d matrix that describes how the variables in the data set covary with each other for that particular Gaussian element. Like, for example, if we come back here, this is our covariance matrix, sigma, and these values are giving you an idea about how, for here we have the x1 and x2, the correlation between these two variables, okay? So this is an example that gives you, given the dimension here, it's like, if we consider the 2D space, it's 2 by 2, okay, matrix, like you can see in this example. Next, we have the omega, which is the mixing coefficient. It's like a weight. And now if we start from this and we are going to keep only talking about weights. Like, for example, in CNN, you're going to say only weights, or so it's here the mixing coefficient. So it's a coefficient that you are using to multiply, and here given each component, okay? So the mixing coefficient here represents the proportion of the total data that is expected to come from the kth Gaussian component. So in this case, we are going to illustrate, not just to put it all together in the formula, or we are going to come back and see what, for this particular formula of the mixture models of the k Gaussians, what each element refers to. So if you can see here, this omega, here it's W. So omega is almost quite similar to W. This is why sometimes it's called the weights, but it is the same thing, which is omega, okay? So this is the prior probability or the weights of the gth Gaussian component. And the rule says that this must satisfy two conditions. The first one, if I have k W's, means k weights, okay, or what we must have is the sum of all of them must be equal to 1, and each of them, the value must not be less than 0 or more than 1, okay? So between 0 and 1. The second thing, if we are going to express the probability given like in a mixture model of k Gaussians, it's expressed like this. And so besides the sum of these weights, like these weights are, as we said, it's a coefficient. So it's multiplied by what? By this function n. N is the normal distribution, okay? So this one, we already seen how it's expressed, okay? So this is the expression of the multivariate Gaussian description in this case. So this is how we move. Now, if we want to see a representation of an example, let's say, of a Gaussian mixture model of two components, what we will have here, two components means I'm going to have two Gaussian distributions. The first one, this is my the density function or the Gaussian distribution of the first cluster, for example, or the first element component. This is the second distribution, which corresponds to the second cluster. If I want to visualize my mixture model, means mixing both, the mixture model is going to give the blue plot, okay? So this is the case. We can see this in bigger space, like this case, for example. It's similar, like if you're seeing some in forest, or someone is putting sand in some way, or this is how it's like. There is not only one, but at the end it seems like one, okay? So there is the mixture, but if you are going to zoom, there is more than one component. So in this case, in both cases, there is two components. But here it's in A, it's very clear that there are two components. Here, the two components are having similar, like, let's say, they are similar shape, okay? And so still, it's a little bit hard to distinguish, okay? So the mixture is almost covering both, okay? So this is an example. And if we come back now and make it simple, the previous example. If now I have a set of points, so what we see here is we were discussing that if I have three clusters, before it was green, red, and what other? Blue. So now we are going to simplify things. We're going to have only two clusters. So the idea is that, let's make it red for yellow, because we don't have yellow one. Okay, let's suppose that what I know is only these points, okay? And somehow here, I know that on the other side, or belonging to the second distribution, I have these points. Now, can you generate from this? So these points, if you can see, it is, or it is plotted really, it's a monodimensional data. So this all is the 1D space, okay? So you have one axis, okay? It's the x-axis, okay? So here, can you guess only from this? You don't look there. So only from points. You only imagine having the points with different colors. So it's going to give you the information that these points belong to two different clusters. This is what I can know. Can you imagine the shape of the distribution?
Yes.
Yes, you are very strong. So how?
From the distribution of the points, you can, if we have
Calculating mean.
No, what can stop you? Yeah. What can stop you of imagining this one like this and this one like this? Nothing can stop me. I mean the exact.
have in the middle.
No, we don't have.
Yeah, you can imagine that for this there will be one distribution, for this and for this there will be one distribution. But the exact shape of the Gaussian distribution, you cannot imagine, expect if, yes,
Mean.
you compute
Mean.
the key parameters for the distribution, which are, I need to compute the mean, which is mu value, and I need to compute the covariance. Great. So the mean, as we mentioned, so I have these points, and I know that, for example, this one starts from 0, so this one having 1, 2, 3, 4. I know the coordinates exactly, okay? From these coordinates, I can sum that, divide by the number, and I can find the mean for the yellow points, because I know their color. I know they belong to one cluster, to a given distribution. And for the blue, also, I'm going to do the same. I'm going to compute the mean, okay? Next, the information that I need is something about this sigma power 2. So, yeah, how I will calculate that? Given I have it now, mu, I know the mean. So each time I'm going to have my coordinates, I'm going to do minus this mean and square plus, okay? And then I'm going to divide by the whole number of samples. So like this, I can just draw my distribution if I have these two parameters, okay? So now, if you are going to imagine the different case, which is, I have the points, okay? But let's suppose that in the first case, you have the points, right? But there was one additional information, which is the color. And the color is giving you information about how many clusters. And when you are utilizing this information, it was allowing you to know the number of samples for the first cluster you are using to divide for both cases. And for the second cluster as well. But if I am going to give you the same distribution, but I'm not going to specify for you the colors. So I'm going to tell you, okay, let's say this is your population. And can you guess whether a given point, it's more likely belongs to the here blue or yellow, for example, respecting these colors for sure. So how can you do that? So imagining, it's not only by imagining things, it's not possible. Okay, we need to compute things. Okay, if you are computing, you always need to profit from the available information. If I have information about cluster, number of samples, coordinates of points, then I can do something. Now, clustering, how many clusters is a very important missing point. So how can I do that? Still possible if I use some rules, okay? If I use, for example, some probability rules from the rules that we see. I am going to compute the probability of that, for example, it's blue given that point, and that point given blue, okay? We have seen things similar to this in probability class. And then you are going to do a whole mathematical like computation to finalize the probability that this point, for example, belongs to the yellow is this one. Probability that the blue belongs is this one. And based on the probability values, you are going probably to guess, find them belonging to two different things. And from two different things, you can say that there are two different clusters. Okay, once there are two different clusters, I have the probabilities, then I can use that position of the elements to guess the shape of that distribution, knowing that it's a Gaussian one. Okay, so it always depends upon from your scenario. Now, this is our problem. So, and I'm making it very simple. Now, given your data set, you have points X 1 to xn, for example, following probability of Gaussian mixture like distribution, what will happen? We are going to estimate that set of parameters I have previously introduced that is having mu, sigma, and omega. Okay? So for each component of the mixture, because the mixture could be having multiple components, the components do not feel lost. This one is having 2 components, this one is having 2 components. So working with 2 components, the easiest case means we have 2 clusters. We cannot work with less. Otherwise, you have only one Gaussian. There is no mixture in the story. Okay? So what we have here, the solution for this is, now I'm going just to introduce the concept. It's the technique of maximum likelihood. So the maximum likelihood, we were discussing before about likelihood, right? In the probability. So the likelihood of belonging means the probability with which that the belonging or not, okay? So it is likely cluster 1 or cluster 2, or mainly it's, let's guess, given the probability, it's going to be, I'm going to maximize the chances, so it is the cluster 1, okay? So here, how to do this? We need to maximize the likelihood of this probability of x given theta, and given the data with regard to the model parameters, okay? What we will do here, theta this we need to optimize, and in this particular case, how, when I say optimize, is to maximize the likelihood, okay? How to maximize is to use the max function. If I have a set of things, I want to find the max, I use the max function. Now, you know the argmax, the difference between max and argmax or not? So when I have the function now, I have my function, okay? Let's suppose that f of x, and we are always familiar that x is the x-axis, the f of x is for each element x, what is the function is giving, okay? So if I have my x here, for this one, for this particular element point, okay? I have the function is giving me, let's say, 10. Okay, so the function gives 10. And the max, if I have these elements, for example, one of them, the function for first point, it's, for example, if it's 10, so it makes sense that this one could be 4. And then this one, it must be in the middle, somehow like, let's say 8. Okay? So I have 3 points, okay? For each point, the function given me that this point is having this function value, which is, I have multiple. Now, what I want to maximize this function. How to maximize? I'm going to choose the maximum value, okay? Which is in this case, 10. Now, here, these are my elements. So this is x1, this is x2, this is x3, okay, in the order. Now, if I tell you 10, can you guess who is this 10? How did you do that? So the way that you are coming back and finding that this 10, refers to x2, this is how you are doing the argmax. Means I'm coming back and this max value is corresponding to this point. So this is the idea. Is that clear? Okay. The argmax must just like for the maximum, it belongs to this point, for example. Okay. Of this probability function p of x given theta, which could be written as the hair product of the all probabilities. Okay. And we've seen this before. So now what we will do is that the maximum likelihood estimation is the frequentist approach used to estimate the optimal parameters related to a mixture model. Given a sample data of data set, the maximum likelihood estimator calculates best values of the mixture model. Here I'm calculating only one value, which is the best. Could be a set of best values, okay? So in practice, the likelihood function is created based on probability density function. So, and it is required to maximize the log related to the likelihood function. So the likelihood function is given by ln of the likelihood function. At the end, we denoted by L. Okay. So now we are moving from the maximum likelihood estimation. So note this, whenever you will see NLE is the maximum likelihood estimation. Now, from the maximum likelihood estimation, this particular, I'm going to call it bridge, okay? It's taking us to another important machine learning algorithm, okay? But before that, this is it's a very frequent principle that suggests that given a data set, the best parameters to use are the ones that maximize the probability of the data, okay? Which is in this way, or in a way, formally pose the problem. Just it's approaching it theoretically, okay? In the particular case now, how it really works? It works given two contradictions, which is at the same time, I'm going to expect something, and given my expectations, I'm going to maximize the probabilities. So this will take us to the expectation maximization algorithm, which is solving this problem that is proposed by the ML. So the expectation maximization algorithm, as it mentions in the name, so it's based on two steps. Step one is expectation. Step two is maximization. Okay, we will detail this step, so don't worry. Which shows if I have between sometimes expectation, sometimes maximization, sometimes expectation, sometimes maximization. So it is an iterative method that is used to do the same to maximize the log likelihood. Okay, is that clear? Online. Okay, great. So the EM for me is a very, very important algorithm. So if you are studying an AI or machine learning class and you didn't see one of them, EM or the PCA, so you didn't study machine learning, didn't study AI. I know that machine learning classes usually teach the PCA. So EM is one of the algorithms which is extremely important in AI, but unfortunately sometimes it's not taught. And I know why. It's in general not taught, maybe because there is a lot of mathematical background behind, and probably professors don't want students to hate their subject, which is not my case. So I want to tell you this is AI, and I'm sure that you will not like this. I need to show you the truth. So there will be lots of math, but at the end we'll be able to understand because this concept is very simple. It's an iterative algorithm that is widely used for optimization problem. And if you're doing AI, you must see, because one day you are going to meet. So this is used, we said, in optimization problems, particularly when the objective function has complexities such as maximizing the log likelihood. So this is one use case, or the most used case. So expectation, maximization, the two steps. Let's denote expectation by E step and maximization with M step. So what will happen is iterative algorithm from expectation to maximization. Expectation of what? Maximization of what? This is what we are going to see now. So the expectation step is given the current parameters, and we see that theta parameters, which are having what are our parameters? Still, we are not leaving the AI class. So the parameters are mu, sigma, and omega. So we are always estimating these parameters all the time. Okay? So given the current parameters of the model, so we have a model with some current parameters, and we are going to estimate the probability distribution, just an estimation. Now, given the current data in the maximization step, we are going to estimate the parameters with the main object is to update the model. So each time you are going for the E step to update variables, which are the parameters. And in the maximization step, you are updating hypothesis. And again, updating variables, updating hypothesis. Okay, until convergence. Okay, so we will go more in depth where in the expectation phase or the expectation step, we are going to use the current estimator for the parameter to create function for the expectation of the log likelihood. And for the maximization, we are going to compute parameters maximizing the expected log likelihood found on the E step, which means, let's start, okay? We have our distribution like there, for example. We are going to have initial values. How to initiate these values? How we did that before? In the k-means, for example.
Using the parameter. Using the parameter.
No. Given the k-means, how did you initiate your, for example, clusters? Or clusters position? Or how did you do that? You know something in the start? No, in the start, first step.
Didn't we just make it up?
The first step,
I
how
thought we picked like the central point.
not really. In the k-means, if you remember, we were initiating and then computing distance and then updating the position of centroids. You remember that?
Yeah.
But the main problem in the limitation of the algorithm was how to initiate. And we were discussing this. How did we initiate? We decide about k, for example, 3 clusters. K is equal to 3. Okay? And then when I'm going to put the position, it's going to be
Random.
random. You will have extra points. And believe me, I don't forget any extra points I'm giving. Last time also Cole was having extra points when he was helping with the algorithm. So whenever I will be mentioning your extra points, maybe you'll say, what is this? But there will be a robot that is going to give you extra points. So random. And randomness, it's a very, very critical point in most of the algorithms. So we know how to do something. We know we are going to apply expectation maximization. One of them, for example, it's going to focus on like expectation step and then maximization step. But okay, before entering to this loop, how I will start? What they say, started as it is, and then it will converge. And this started as it is randomly makes a lot of problems, and we will discuss this. Okay, so there is an initial values, let's suppose, without discussing the details. Next, I'm going to keep applying expectation step, maximization step, and next I'm asking, is it converged? If not, I keep doing this until convergence. And when I'm going to converge, I'm going to stop, which make you remember the steps of k-means, right? But the algorithm is working in a different way. So like you mentioned, the first one is used based on similarity and distance. This one is based on probabilities and log likelihood and many other things. So now our problem now is still, now we have these model parameters. We have, this is our observed data. And we have also some ik here, which is a hidden latent variable, which is related to now to xi. And this is equal to 1 if xi belongs to that k cluster component of the mixture, otherwise not equal to 1. Okay, this is how we are going to think. So can you think of the steps of this algorithm? So the k-means algorithm is how many step algorithm? Simple, it's 4-step algorithm. So it's also similar. Here we have a 4-step algorithm. The first step is to initialize these like theta parameters of the model. The second step is the expectation step, the E step, is to find the posterior probabilities of the latent variable z given current parameter theta. And next I'm going to maximize the chances. So it's a maximization step, M step, to re-estimate the parameter values given the current posterior probabilities that I'm finding in the previous step. So here I use this to compute the value of z and re-estimate theta. So I keep doing or iterate steps 2 and 3 until convergence. Okay? Before, what we do is we compute the distance and assign each like centroid to the most near point and keep doing this until convergence. And the convergence, which means like it's not moving anymore the clusters. And here I'm going, and here it's similar to the K. Okay. Here, what we have, it is in more depth. And when I say in more depth, here I made it simple. So what you will see now in these slides, I'm showing you the truth. Okay, this is a good thing, but I cannot show it to you the way I have seen, because the way I've studied the EM algorithm, I will take you straight to that way. So the way I've studied the EM algorithm was like this: a lot of math and a lot of equations, and it's written just in the board. There was no like writing any supports for that. And this is the EM algorithm. Enjoy. Okay. So at the end, I forgot all this equation. And I'm honest with you, after 10 or 8 years, who is going to remember all this? So no one. No one. Okay, I will remember whenever I will be preparing it for an A class, but not really. Okay. So the thing is that for me, how to learn an algorithm, first, you must not be afraid from that algorithm. Whatever the complexity of the math behind or the code behind or the idea behind, you can summarize it in a few steps. And this is what is like the truth. So the truth is that we are seeing this EM algorithm as a start, just 2 steps. Then we are zooming on these steps and we are zooming more. So at the end, you know what is waiting for you, okay? But let's keep it simple, okay? So if, for example, I have my EM algorithm for GMM, first step is I'm going to initialize mu and sigma. I'm going to give random values. And then the E step, which is to fix mu and sigma and update the ZKI, okay? This one we are just introducing here, which is the latent or the hidden variable, okay? And now, once we are doing that, so what we will do, we are going, this is updated in the step. Now we are going to do the opposite. We fix this and update the parameters. We keep doing this, which is shown here, like each time, one time we're updating variables, one time we're updating hypotheses, okay? So we keep doing this, and how to do this? For each one, we have the formula. The formula is mainly based on probabilities that we see first time, based on base rule. And this is always the key behind any formulas that you may meet in this context, okay? So, and at the end, we stop when we are converging. So I didn't generate this picture. I'm taking from here, this link. And in this link, I found something really interesting, I want to share with you as well, which is a real use case of the expectation maximization algorithm. So in this case, so for sure we applied on a Gaussian mixture model. And when we say mixture model, we know that there is more than like one Gaussian within the mixture. So one application case is to detect outliers. And as we said last time, outliers are these elements that do not belong to the group. Like in this case, it's clear that the outlier is not the green apple. It's here the orange color of this orange, for example. So in this case, so you see the application, it depends on the model. And we are going to discuss this, but I just want to show you behind all that math, you can see something. So this is a real world application that is not only that we are going to study the equations and all. So to apply whatever your algorithm, you need to respect your data. If you have data like that, it's just 1D data. You can apply it in bigger spaces. And in this case, you are having, what is the space in this case?
2.
Not 2. We have the RGB.
3.
Yeah. Okay. So 2D is when I have only X and Y here. and there is no colors in the story. If I'm going to consider the color space, there is many color spaces. There is the grayscale, there is the RGB, there is many, but if we respect to the RGB, you can see the red, green, and blue. So each of them represents one dimension. And here, so you have initially 3-dimensional Gaussian models, which are, you know that a given pixel can take the maximum value 255 and minimum it can take 0, okay? So the red is the first one because it's R, so it's taking the maximum here, 255, and both other elements 0, 0. For the green one, it's taking the maximum for the middle value, which is the green, okay? And for the blue one, which is, the blue one, which is going to take 0, 0, 255. Is that clear? So what we have this information, mean vector, along with the random covariance matrices that are going to be used as initial models, okay? Then we keep applying the E step and the M step until convergence. And convergence, it means that there is no change in the estimated parameter values, okay? Next, first the step, which is the expectation step, the E step, is used to compute or normalize probability of assignment of each pixel. So we want to know each pixel belongs to the red, to the green, or to the blue channel, okay? And after that, the maximization step is used to obtain the MLE, which is likelihood estimation. Great. So for the parameter mean and covariance matrix of each of the model as weighted average contribution of the data points, and at the end the EM algorithm for GMM is shown as below. So this is from where I took this picture, which shows at the same time a real-world application case, also the different steps with the maths behind this, okay? And the math I'm keeping in the appendix at the end, where you can read, and if you are understanding the whole concept, then you can understand or enjoy understanding the formulas, okay? So this, once we apply, given here, you can see the number of iteration, for example, the first, the second, how the GMM with the apples orange image is performing, okay? So you understand here the Gaussian distribution for this one, it's the orange, and this is for the green, and from the start how it was randomly initialized, and each time we are applying the expectation maximization step until convergence, okay? So this is just an idea. So EM algorithm, when it convergent within 12 iterations, for example. But it's not enough only to have the algorithm. As I said last time, we have data, we need to turn into information, then information into insights. So the idea is, for example, if I don't need my outlier, then I'm going to give the value black, and then I'm going to remove this component. So mainly it's like this, how in Photoshop one element is removed. This is a very interesting use case of the EM algorithm, okay? So any questions? Online? Okay, so now once it's clear the idea of this algorithm, at least how it works, how much useful is it, and the basic or simple steps for it. Now let's take for sure more in depth, because we are going to reach to very deep point, but now we see with an example. So given this example, when you see like this, it means a Gaussian, okay, representation. So with here you see it's more like in the bold line, because this is the top, and the more it's going far from the center, I'm going to say, or the mean is getting less dense, okay? So it's, you can imagine this is a Gaussian distribution A, and the second cluster is given by B, okay? And this is the whole mixture, okay, together. So now what we have is hidden variable for each point which Gaussian component generated. So we have the A and B, and we have the data sample. The expectation step is going to be, for each point, I am going to estimate the probability that this point, or the probability that each Gaussian has generated this point, which means for this one, I'm going to compute the probability that this point is generated by the Gaussian mixture A, and also for the same point, I'm going to compute the probability that this point is computed by this Gaussian B, okay? So for example, probability that is generated by A, it's 0.6, by B, it's 0.4, which makes sense. It's, let's say, more near to these points where A is generating, So for this one, if I'm going to compute these values, I'm going to find that the probability generated by A, which so far is less, which is 0.2. However, the probability that's generated by B, it's 0.8, which makes sense because it's more near to the Gaussian B. So the second step, so this is expectation. Expectations means what? Expect something. So expect what's something you can expect in the A class? You can only expect probabilities. So here you are expecting the probabilities of that belongs to the existing Gaussians. It could be 2, it could be 3, it could be 4, whatever. Okay? Now expectation is done. I have something. It's not the final thing because there will be a loop, but I have something. Now I'm going to maximize. What I will maximize? Given the current data, which is the probability of A belonging to A and B, estimate the parameters to update the model. This is what we will do. Okay, so this is going to be the fact. I'm going to estimate the parameters to update the model. So this A is initially where? Here. And most of the points are where? Are here. You can see the points. This B is here. It could be even, I don't know, it could be even here. Because it's random where it's there, the location of this. So it's here. Most of the points we are finding probability of B, they're here, for example. So what we will do, this, let's say, distribution, I'm going to update the parameters. And you know the parameters, they are the mean, means the center of that representation, for example. They are the covariance matrix that is going to give you an idea about the representation in the space, how these Gaussians are represented, and what else? The omega, which is the factor, okay, which is the weight, okay. So now this will make it more near to the most of the points, but still this is not the final step. I keep doing this until it's converging. So I'm going to find this A, for example, is here, and this B is here, for example. Okay, and like this, I can say this cluster is the elements belonging to cluster A, and these elements are the elements belonging to cluster B. So the expectations to expect for the data, the available data, the belonging to each distribution, and the maximization is to maximize my parameters so that they are adapted to this information I am calculating. Okay, so this is the expectation maximization algorithm. Okay, now let's discuss the difference between k-means and this Gaussian mixture, for example, the GMM. What I was teaching today is the GMM, so I am eligible to tell you what is that about. The GMM has as objective function to maximize the log likelihood, which means the log likelihood is the function. For example, I'm maximizing this. The EM algorithm is mainly a four-step algorithm. After the initial step, which is a problem, we don't discuss that, we have E step and M step. The E step is to compute the posterior probability of membership, and the M step is to optimize my model's parameters. Then I perform soft assignments during the E step. I keep doing this until convergence. This can be used for non-spherical clusters and can generate clusters with different probabilities. So it's a powerful algorithm. We see a use case or an application for object removal from a given picture, for example, removing out layers. Now you are going to have, let's say, 5 minutes or 10 minutes to think, or maybe come back through the slides. I was uploading the slides of K-means, right? You go through the slides of K-means, or even try to remember what we see in K-means algorithm. Try to check each time, what is the objective function here? What is the correspondence in this case, in the algorithm main steps? And what is the difference between K-means and this one? Let me just check if I am uploading. In general, I upload the recordings, but now let's. Okay, I will upload that. You can start thinking of it. I think. Okay.
I have a quick question while you're uploading that.
Yeah, sure.
So originally on the schedule, I know it was planned to have an exam, the second exam next Wednesday. Are we still having that or?
Even if we will have that, it won't be in the planned lessons, because in general, for me, the main thing is to learn new things. So for me, the exam is not that much important thing. For you, I'm sure it's very important. This is why I am really careful with exams and with grading and all that things. So from your side, don't worry. From my side, I want to teach you more. So I see like 2 classes, one for the review, one for the exam. Would be like 30 minutes for the review, and then you may have it online, which is going to be a very simple exam as compared to the previous one. It's going to be just a quiz. It's going to be just to test your knowledge about the machine learning algorithm part. So mainly you see KNN, maybe I can give you things about that, the Gaussian mixture. I want to complete this part and then we have it. So I would absolutely tell you 1 week before, and I'm going also to prepare you for that. Like if it was preparing in one section, I can do that. If it's just 3 minutes, I will do that. So do not worry. It's not for the upcoming minimum 1 week, but just keep in mind we are going to test knowledge about this part. That is it. Okay. Okay. Okay, so it's there, learning one. If you need the key means. So sometimes I am going to put the PPT, and whenever I'm putting the PPT, so means there is like algorithm steps or something to see. If there is no PPT or PDF format, means there's nothing to show in that course. Okay. Are you done? Online. Okay, then great. What is the objective function of the k-means?
Minimize the distance between.
Classify, classify the data.
There is a crime. Now, I know someone called the DPS. We are still in the clustering part, is talking about classification. So these concepts must never, ever, ever be mixed. Classification is something related to supervised learning. Is there any supervised data here? No. So this is the case of unsupervised learning. So we don't talk about clustering. We don't talk about classification. We talk about clustering. Okay? So think of it. No, he was going to say something, but he said classification. Now we can come back to your original idea, supposing that clustering is the right word. Yeah?
Like partitioning the data sets into k distinct clusters.
Objective function is like this is my final object, and it always needs like what optimization part. Means something that I need to make it perfect.
Yes, so we need to minimize the distance between the points within the same cluster, and for this.
Yes. So when we see the k-means, if you come back, and I can do that, we didn't. So we see the k-means here, and this is when we say that the k-means is going to stop. It's going to stop given criteria, and this criteria is the sum of the squared errors. And this sum, it depends upon from the distance. So mainly, we are not minimizing the distance, we are minimizing the criteria itself, which is the function used for the evaluation, which is in this case the squared errors. So given the particular case when we are using Euclidean distance, for example, our objective function is to minimize the sum of squared Euclidean distance, okay? Because each time there is like a function, and this function is not just a simple scalar, which is distance value or something. No, there is a function, and there are many like functions to measure the error. We can take a look on performance and error measures, but this one, which is the squared Euclidean distance, is the very famous one. So this is the only one that I was mentioning in my slides. However, there is like many ways to compute the error, okay? So in this case, we use only this, okay? However, given different algorithms, we can have different error functions, and we can each time optimize this error function, okay? So if I ask, and there will be a quiz, and I don't ask, okay, I ask a lot of simple questions, but one single question that can distinguish, okay? So when you are taking the exam for the next time, don't sleep when there are many easy questions, because one question will be there only to test something and I will disappear, okay? Okay, so now the k-means now itself, it's based on, like you said, Farah, I have clusters and I'm going to update the position of these clusters so that each cluster is like is centroid, sorry, is representing, or that cluster is converging. It's not like moving anywhere. So it's there where we stop. Now, given this knowledge about the k-means, we can use it or optimize it by using the EM. Because if you can imagine in both scenarios, you have this case centroid, okay, and you have data points. So how you can think about like optimizing the k-means using EM algorithm, you use the expectation step to assign points to clusters, right? We did this before with a simple distance, but we can include that in the expectation step, okay? The maximization step, the M step, is going to be used to optimize the clusters, which is a great way to merge both of them. And this way it performs hard assignment during the E step. So in this case, we assume the spherical clusters with equal probability of a cluster. So you see, whenever we are seeing one algorithm, there is a similarity with the previous algorithm, and there is a way to profit from what we see in the new algorithm, okay? So I don't want to say my AI course is good, but you won't see this everywhere, okay? There is a link between algorithms. So, which is now, to sum up, the GMM, it's a strong algorithm. This is why even we are using it probably to make k-means perform better, okay? So it has its strengths, which include give probabilistic cluster assignments, have probabilistic interpretation, and can handle clusters with varying size and variance and so on. So this has great points, but it has its weakness, okay? Otherwise, there is no need even to use any method, okay? Or there is no need to study other algorithms. The weakness here, which is mainly also there with the k-means, which is the randomness while initializing things. So it's an initialization matter, and also choose appropriate distributions. And there is the problem of overfitting as well. Overfitting is a huge problem. Okay. Okay. So I think now we are done. I am going to keep you with this appendix, which is going to, it's a very detailed story. You can read it as a story before sleeping tonight. It's your story for the night. So because the way it's written, I'm loving, otherwise I won't answer or put in my slides, okay? So it's going to show you exactly how to start, how to go through the rules, how to use the Bayesian rules, how to use the basics and things that we already covered to reach to the point where we can like write the final formula of, for example, the expectation maximization, the likelihood, how to maximize the likelihood and express that in terms of maths and so on. So this is very important for you to read, and that is it for today. Okay? If you find any problems here, you can contact me. Otherwise, the way it's explained, so I think it's enough. Okay? Any questions? So great. I see you when next time. Okay. About grading, it's going to be this weekend. Okay. Maybe if it's good, I will share it in the weekend. If I may see some like bad grades, I'm going to update that on Monday, but not after Monday. Okay. I'll see you. Okay. Stop sharing. We are not sharing. Okay. Stop recording.